Hello everyone, welcome to Civil Engineering and Stuff. And in today's video lecture, we are going to do a numerical on the topic irrigation efficiency. So in the previous lecture, we have discussed about the variety of irrigation efficiency, that is the water conveyance efficiency, water application, water storage, and likewise. And we have done a brief numerical on the water distribution efficiency for a better understanding. All right, so here in this lecture, we are going to do another numerical that will cover up all the different type of irrigation efficiencies. So if you haven't watched that lecture, it is recommended to first of all watch that lecture for a better understanding of the different type of irrigation efficiencies, and then move on to this numerical. Otherwise, those kind of basic concept won't be clear to you. I'll put a link of that video lecture here in the cue card as well as in the description box. All right. So if you have watched and the concepts are clear to you, then let's move ahead and solve this numerical. Now the question is that there is a stream of 130 liter per second which was diverted from a canal, and 100 liter per second what uh, were delivered to the field. An area of 1.6 hectares was irrigated in 8 hours. The effective depth of root zone was 1.7 meters. The runoff loss in the field was 420 meter cube. The depth of water penetration varied linearly from 1.7 meter at the head end of the field to 1.1 meter at the tail end. The available moisture holding capacity of the soil is 20 centimeter per meter depth of soil. It is required to determine the water conveyance efficiency, water application efficiency, water storage efficiency, and water distribution efficiency. The irrigation was started at a moisture extraction level of 50% of the available moisture. All right, this is the question. All right, so let's see what we have to find. We have to find the water conveyance efficiency, water application efficiency, water storage efficiency, and water distribution efficiency. So let us find each. So let's first of all find the water conveyance efficiency. Water conveyance efficiency. And the formula for water conveyance efficiency is the water that is diverted from the canal, water that is diverted from the canal to the total quantity of water that is delivered to the field into 100. All right. So here in the question we can see that we have stream of 130 liter per second of water diverted from the canal, and out of this 130 liter, only 100 liters per second of the water was diverted to the field. Values are given in a very straight away format. So the water conveyance efficiency will be water diverted from the canal is 130 liter per second. So this will be 130. Water diverted to the field is 100 liter per second. And since the unit is same, so we need to do very much into 100. So solving it, the value will come out to be almost 77%. Okay, so this is the answer for the first type, the water conveyance efficiency that we have found. All right, keep solving as we move ahead. I highly recommend that you also sit with a calculator, with a notepad and a pen, and you have the question in front of you. Pause the video, try to solve the question by yourself, write down the formulas, try to solve the question by yourself, and let then move ahead and just see if your approach was right or wrong. All right, that's when you will get to know if the concept is clear to you. All right, then the second thing that we have to find, the second type of efficiency, is the water application efficiency. Now water application efficiency, the formula for water application efficiency. The formula for water application efficiency is the total quantity of water that is delivered to the field Total quantity of water that is delivered to the field to the water that is stored in the root zone into 100. This is the formula for water application efficiency. Now, if we observe the water delivered to the field, we have been provided that is 100 liter per second. Let's write it down. The water delivered to the field, the given parameter in this case, the water delivered delivered to the field is 100 liters per second. Is 100 liters per second. And what is the do we have been provided with the water stored in the root zone? Let's see, an area of 1.6 hectares, effective depth of root zone, runoff losses, etc. etc. So, not a direct value of the water stored in the root zone is given to us. Correct? Just like unlike the part 1 where both the values were directly given. Here in part 2 of the question, the water application efficiency, we are not given the water stored in the root zone parameter. We have to find out the water stored in the root zone. And we have discussed in the in the previous video that this water stored in the root zone is that out of the total quantity of water that is delivered to the field, total quantity of water that is delivered to the field. Now, once the water is delivered to the field, the water delivered to the field is 100 liters per second. This is the discharge at which the water is being delivered to the field. Now, water is applied or the irrigation is done. Now, once the irrigation is done in the field, so what will happen? Part certain losses will take place, some evaporation, percolation, and likewise some losses will take place. So, after the loss, there will be an actual quantity of water that the roots of the plants will use for their to fulfill their nutrition value. Correct? So, out of the total water that is delivered to the field, there will be losses, and after the losses, there will be an extra quantity of water that is stored in the root zone. So let's see if we are given some losses. Yes, we have been provided with a parameter. The runoff loss in the field was 420 meter cube. Okay, so the runoff loss is 420 meter cube. This is the runoff loss. All right. Here we see that the unit is 100 liters per second, while the runoff loss is 420 meter cube. Correct. So definitely we cannot subtract 420 from 100 liters uh, per second. Correct. So we need to change either this 420 meter cube to liter per second or 100 liter per second to meter cube. And I believe like doing this is much easier than converting it into liters per second. You can try it by yourself and you can see the number of steps that will take, or like it will take too much time to convert this meter cube into liters per second. All right. So one thing is clear, like since the unit is 100 liters per second and here the unit is meter cube, so we need to have a homogeneous unit. We are looking into converting this liter per second into meter cube. All right. How do we convert this liter per second into meter cube? First of all, let us understand what this water delivered to the field is. The water delivered to the field is at the rate of 100 liter per second. That is in 1 second. 1 second, 100 liters of water is being provided. All right, this is the meaning. Now let's move to the question and see what are the other parameters that are given. So we have been provided an area of 1.6 hectares was irrigated in 8 hours. All right. So an area of 1.6 hectares was irrigated in 8 hours. The effective depth of root zone is 1.7 meters. The depth of like the runoff loss is 420. Depth of water penetration varied linearly. So this value will be used in water distribution efficiency, not much required. Available moisture holding capacity is 20 centimeter per meter depth. All right. Now, if you observe, our goal is to convert this liter per second to meter cube. Correct? If you see here in the question, Just think how we will convert this liter per second into meter cube. Pause the video, think about it, try to get a value in meter cube, and then resume watching the video and see if you have got it right. Okay, so I hope you have done the same. Now, here we are given that an area of 1.6 hectares was irrigated in 8 hours. So the overall area of this land is 1.6 hectares, and the water was delivered to the field for continuously 8 hours at the rate of 100 liters per second. So in 1 second, 100 liters was supplied, right? So in 1 second, in 1 second, in 1 second, the quantity of water supplied was 100 liters. So in 8 hours, or 8 into 60 seconds, how much quantity of water supplied? 100 into 8 into 60 into 60, right? This much liters of water was supplied. This much liters of water was supplied. And we know 1 liter is equals to 10 to the power minus 3 meter cube. Just remember it, it's a very important unit conversion. We have discussed it before, that will be used frequently in irrigation or in other mathematical also. So the quantity of water, the quantity of water supplied in 8 hours at 100 liters per second will be 100 into 8 into 60 into 60 into 10 to the power minus 3. So this will come out to be 2880 meter cube. This will be 2880 meter cube. So the overall volume of water delivered to the field is 2880 meter cube. Same thing here. This is in terms of discharge. This is in terms of volume. Now, if you observe that we have now made both the units homogeneous. So this much volume of water was delivered to the field. This much volume of water was delivered to the field for 8 hours. Out of this, 420 was lost eh, as a loss in the form of runoff losses. Correct. So rest is the quantity of water that is stored in the root zone. Therefore, the net quantity of water, net quantity of water that is stored, net quantity of water that is stored in the root zone will be 2880. That is the total quantity of water delivered to the field minus the overall losses that has encountered. Right. So this will come out to be 2460 meter cube. If in the question there would have been some other losses like evaporation losses, percolation losses, then those losses would also have been subtracted from this value. Alright, since here in this question we have been provided only one type of loss, that is the runoff loss, so we are subtracting only this. If there would have been other losses, we would have subtracted those also. Now, if you see, we have the water delivered to the field, water stored in the root zone. So this water application efficiency, the water application efficiency NA, water application efficiency NA will be 2460 divided by 2880 into 100. All right, so this will come out to be 85.4%. This will come out to be 85.4%. This is your water application efficiency. You have found out this also. Now, what is the water storage efficiency? water storage efficiency. What is the water storage efficiency? And water storage efficiency is the ratio of the it is the ratio of the water stored in root zone to the amount of water or the amount of moisture required to bring moisture level back to field capacity back to field capacity. We have discussed what the term field capacity means, so it's very important. If you should know all these technical terms, it becomes easy for us to interpret the values that are given to us. All right. So water stored in the root zone. We have found the water stored in the root zone, right? We have found out the water stored in the root zone in the previous part. And we need to understand what is the water required to bring moisture content back to its field capacity. And for that, you should have a clear understanding of all the moisture levels in the soil that we have discussed in the previous lectures. All right. Okay. So just again pause the video. First of all, if those terms are not clear to you, reread those terms, understand those terms, look at the values that are given to us, and see how can we find out this moisture content required to bring the moisture content back to its field capacity. Right? Pause the video, look into this, and get a value. Right? Try to solve it by yourself, get a value, and if you encounter any doubt, just then after that resume watching, and if you have any doubt, you can always ask in the comment section. Okay. Okay, so I'm hoping that you have done the same. Now let's solve. First of all, this is the ratio. So we have the water stored in the root zone. This parameter we have water required to bring moisture content back to its field capacity. The moisture content of the soil back to its field capacity level. Hmm. Back to its field capacity level. So let's see what are the parameters, what are the values that are given to us. All right. The available moisture holding capacity of the soil is 20 centimeter per meter depth of soil. This is one value that is given to us. All right. The moisture holding capacity of soil is 20 centimeter per meter depth of soil, and the effective depth of root zone is 1.7 meter. Okay. The effective depth of root zone is 1.7 meter, and the available moisture holding capacity is 20 centimeter per meter depth of soil. If you look into it, this means that we have a plant whose depth of root zone is 1.7 meters. Whose depth of root zone is 1.7 meters, and the moisture holding capacity of the soil is 20 centimeter per meter depth. 20 centimeter per meter depth. So for 1.7 meter, what should be the moisture holding capacity of soil? First thing we should know, because this is what the optimum zone we want. Now, like this is the overall moisture level in the soil up to this depth we want. So the moisture holding capacity, the moisture holding capacity of soil, the moisture holding capacity of soil will be 20 centimeter into 1.7. Why? Because for every meter 20 centimeters of the moisture is being held. So this will be 34 centimeter. This is 34 centimeter. Then we have been given another information that the irrigation was started at a moisture extraction level of 50% of the available moisture. Irrigation was started at a moisture extraction level of 50% of the available moisture. What does this term means? This term means that that as soon as that this is, let's say, a depth of soil, we have this field capacity here, and what happens is watering is done and the moisture content is brought back to its field capacity. Now, after this, let's say the watering was done in day one, irrigation was done in day one, and in the second day, the plants will the roots of the plant will start to absorb this moisture, and the moisture content of the soil will keep on decreasing. Day two, day three, day four, day five, day six, day seven, and like that. And as soon as the moisture content reaches to the 50% of the moisture holding capacity, again the watering is done. Again the irrigation is done, and the moisture level of soil again is brought back to its field capacity. And after that, again the moisture content will reduce. Then again watering is done and it's brought back to its field capacity. Okay, so as soon as the moisture holding capacity reaches to the 50% of this, then the irrigation is done. So the moisture that is already available in root zone, moisture that is already available in the root zone at time of start of irrigation, at time of start of irrigation, at time of start of irrigation will be 50% of the overall field capacity depth moisture. So this will be 17 centimeter. This will be 17 centimeter, right? And that's when let's say the overall depth was 34, overall depth of 34. As soon as it reaches to 17 centimeter depth, the irrigation is. Now this value is for a per meter square area, right? This value that we have got is for a per meter square area. We have discussed this concept in the previous lecture on this topic in theory, as well as when we have find out the field capacity derivation, as well as when we have discussed the different moisture content of the soil. We have discussed that all the discussion when we do is for a per meter square area, and then it is distributed throughout the land. So this is for a per meter square area. 17 centimeters for a 1 meter square area. The area that is irrigated is 1.6 hectares, which is equals to 1.6 into 10 to the power 4 meter square. This is for a 1 meter square area. So for 1.6 into 10 to the power 4 meter square, it will be how much? 17 since it is in centimeters, so 17 divided by 100 meters. 17 by 100 into 1.6 10 to the power 4 meter square into meter. So this is your meter cube. Correct. So I'll just write it down like this. Meter cube. So this comes out to be 2720 meter cube. 2720 meter cube. So this much volume of water is required to bring back the moisture content back to its field capacity, right? I'll again repeat just for your sake of simplicity. The overall moisture holding capacity of the soil in terms of depth was 34 centimeters. The irrigation was done when the moisture content is dropped down to its 50%. 50% means 17 centimeters. 17 centimeters for 1 meter square area. For 1.6 into 10 to the power 4 meter square area, 17 into 1.6. So this is for the overall land area. Correct. So this is the quantity of water, like 2720 meter cube of water is required to bring back the moisture content of the soil back to its field capacity, right? And the water stored in the root zone we have already found that is 2460. Correct. So the water storage efficiency NS will be water storage efficiency NS will be 2720 into 2460 into 100. So the value will come out to be 90% almost. All right, value will come out to be 90%. All right, I hope this is clear to you. If there is any doubt, you can always ask in the comment section. Okay, then the last part is we have found out this one. We have to find out the water distribution efficiency, and we have already done a numerical on the water distribution efficiency in the previous lecture. And uh, here the values that are given to us, the depth of water penetrate very linearly from 1.7 meter to 1.1 meter. The formula for water distribution efficiency, the formula for water distribution efficiency is 1 minus y by d, correct? Where d is the average depth of water, of distribution of water. Here it is 1.7 plus 1.1 divided by 2. So this is 1.4 meter. Y is the deviation from the average value of the depth. So we have y1 as 1.7 minus 1.4. So this will be 0.3. Y2 is 1.1 minus 1.4. So this will be again 0.3. And overall y is the average value. So y1 plus y2 divided by 2. So we have 0.3 plus 0.3 divided by 2. So this will be 0.30. Correct. Let's put the values. So the water distribution efficiency will be 1 minus 0.30 divided by 1.4. All right, so this into 100. So this will come out to be, so this will come out to be 78.6%. Okay, so this is how we find out the water distribution efficiency. All right, so I hope this numerical on the water distribution efficiency, water application efficiency is clear to you. All right. If you have any doubt regarding this, you can always ask in the comment section. All right. Try to do this numerical by yourself again. And if you again have any doubt or any query, you can always ask in the comment section. If you have watched till the end, I think you found the video useful. And if so, like the video and post your views in the comment section. Uh, Subscribe to the channel for more videos like this. Thank you for watching. Have a nice day.